Hey, we're finally here at the last section for Math 1324 for this course. The course is going to be on definitions of the derivative. So, what does the title imply? Okay, so let's look at that first. Let me get my pen working. So the title says derivative. We know that a derivative implies the equation to find the instantaneous rate of change or velocity for any given x value that lies in that function. Okay, so knowing that, let's review a little bit. And in the previous sections, to find instantaneous rate of change, we found the limit as h approaches 0 of any function given some value a. I like to do the derivative first and then insert a divided by h. So this is the difference quotient with a limit implied to calculate the value. Again, I have always used the function itself and then inserted the x value because that is a derivative. All right. Well, we're going to now include a tangent line. Well, what is a tangent line, you ask? All right. Well, let's look at a function here. Oops, didn't get my, hold that thought. So let's look at this guy. Oops. So we have a coordinate plane here, and it's drawn halfway decent, but it's better than me drawing lines that don't make sense. So I'm going to insert for you a function, and I'm going to do an upside down parabola. All right. So if we wanted a tangent line and we wanted it at this point right here, then the tangent line would go right through, right at certain touches. At the given ordered pair given, at that one point, it does not cut it, it does not go through it, it just touches. So we want that definition, and I'm going to kind of write some steps for you. And the tangent line is created from a given x of 1, y's of 1 from the original function And using the derivative value of the function with x of 1 used to find tangent slope. Now, later on, we'll see a very complex looking scenario. And for the present, I'm going to just give you the workable form for understanding. All right, here it goes. All right. So once we find the dy dx function, we insert x of 1 to find tangent slope. So our first step is to find the derivative. The second step would then be use equation of the line, slope, I have it as slope-intercept form. Slope-intercept form with the dy dx of 1 and x of 1, y sub 1. And we've done this one before. And here it is. Y equals, and this is going to be our derivative slope, x minus that x of 1 plus the y sub 1. So we'll be trying to do the easier problems, inserting our values. Let me turn off the sound. Okay. So the next thing I want to cover, and this is important in the sense of understanding which is which. A tangent is at one point. A secant has two ordered pairs. And they are x of 1, y's of 1, and x of 2, y's of 2. And in this one, the derivative, the change of y over the change of x, is determined by the movement of the function from one to another. All right, so a secant line is through two distinct ordered pairs. That have a slope kind of like a velocity by direct line through the 2 points. I know that sounds like gobbledygook, but it's important you understand this in order to do mathematics. So here we have a great picture, and I got this from the textbook. In the first one, we have a secant line. This line has the direct change of the 2 points, point B and point A. And so you can see then that we have this slope in this condition. Now, in this case, the line is the only one that goes for that particular point. Everything else is a secant. And they use this graph to prove to you that the closer we get to instantaneous velocity or rate of change, the better we can adjust to changes in whatever we're building or whatever we're projecting. So that's very important. Okay, so I've given you the groundwork, and we're going to do some examples next.